I think we're ready to go.
We're good to go. Okay.
Hold on a second. Let's make sure they're okay. Well, if we get some indication, send us a message in the text, Michael, if we're ready to go, or give us a thumbs up.
As far as I can tell, I think we're live. Yeah.
Okay, so can you see? Do we have some folks watching?
The
Let's do it.
attendees list says 0, so I'm not sure if anybody's there, but maybe.
I'll tell you what. Let's wait 30 seconds and see if somebody shows up. But if not, we'll get the pictures out and talk some shop.
Talk some fun stuff.
Astronomy stuff is always fun. The good thing is we know it's going to be recorded too, so we can see it later. It's pretty. I actually kind of appreciate these being archived, so you can always go back to them and see them later too.
Yeah.
I know Gabby still said she's in the waiting room, so I know people might be waiting, even though it says no attendees.
Yeah, I wonder if the links are correct. Maybe Michael, take a peek at that real quick. Thanks, Erica.
Yeah, I will look into that.
Okay.
It's nice having backup. Erica, it says are you a student? Are you a STEM major? Are you a
Nope, I just work for the ambassador program. So
Oh, okay, good. So you're part of the ambassador program.
Yeah, just
Oh, that's cool. So they've enlisted you all to come and help with the logistics
Yes.
of the symposium.
yeah, to answer the questions. We've done that a couple times. Gabby said she's in demo 3. I'm
Oh
not
yeah,
sure.
that's the wrong one. We're demo 2.
Okay, I'll let her know.
So as soon as we get Gabby here, we'll go. Me and you.
Okay. The weather's looking good today for solar observing.
Yeah, it is. I saw. Did you see the picture? Alton sent a picture that's got. So looks like we have a couple sunspots and maybe a couple prominences to see.
Yes.
Yeah.
So where are we going to be today? I forgot where it's at.
I think all the equipment's here in my office, and so I think as soon as we're done, you and I'll decide. We'll send an Alton message and tell Alton what time to be here. Maybe 2:30, 2 o'clock, something like that.
Okay.
And then yeah, come on over and we'll get down and we'll set it up over at LLC.
Yeah, we're going to observe some sunspots or prominences.
Absolutely,
cool.
sir.
Maybe give it another minute and just start.
Let's give it one more minute. We're gonna go at 1:05 regardless.
Yeah, the first 2 minutes aren't just pictures. So
It's all good, man. Don't
Yeah.
fuss about it. But we still want to give a little overview of Pine Mountain, so show the pictures.
Yeah.
Yeah. I'll tell you what, as soon as it hits 1:05, we're gonna go. That gives everybody long enough to get here. All right, let's do it, man. Me and you. You ready?
Okay. Yeah.
Well, hi, everybody. Welcome to the demo session number 2. My name is Dr. Scott Fisher. I'm a professor in the physics department at the University of Oregon. And I'm going to introduce you to my colleague who's sitting right next to me on the screen here, Riley Monsrud. And Riley is a senior physics major, also at UO, who is just about ready to graduate here in a couple weeks. So Riley, congratulations on that. That's a heck of a feat. And today we'd like to tell you a little bit about Pine Mountain Observatory. which is an observatory that University of Oregon owns and operates, and a really neat project, research project that Riley and I have been working on for the past 2 years. We just discussed it with each other, and we realized that Riley has been involved with Pine Mountain since the summer of 2019, as a matter of fact. And so, Riley, how about showing us a nice picture of Pine Mountain? Let's tell the audience what it looks like.
So here's one picture,
So-
one of the research telescopes that we have up there, the little clamshell dome.
Absolutely. We've got 4 telescopes, almost 5. And the smaller dome to the left there, you can see is houses our research telescope. And it turns out that the sky is quite beautiful up at Pine Mountain, as you might imagine. And Riley, do you have a nighttime shot that we might be able to show the folks?
Yes. Slide it over here.
Oh, there we go. That's a photograph of Pine Mountain that was taken. Actually, it was taken 4 years ago. It was in the summer of 2017. Excuse me, where we had a UO student named Justin Hartney, who brought his telescope, or excuse me, his camera system up the Pine Mountain, and we got to take this picture. You can see again in the foreground, you can see the domes. You might see a lot of red light down there. So as during, excuse me, during the nighttime, we like to use red lights, so our eyes are better adjusted to the dark. And then that glorious dark sky up above the observatory, including the bright stripe of the Milky Way going across the sky. And we wanted to show this just to give you a little indication of what the sky looks like up above the observatory, and heck, why we built the observatory there in the first place. It turns out it's an extraordinarily dark site. It's also in a really interesting and beautiful part of Oregon. Oh, there's another picture that was taken by a professional photographer named Jack Nichols. And this is a long exposure. And so you see the wiggly red lines. Those were folks who were walking around with red flashlights in their hands. And again, an enhanced version, but a beautiful Milky Way going across the stripe of the sky right there. And so that's as you might imagine, we love having a dark sky with it gives us high quality data that we can obtain with the telescopes up at Pine Mountain. And Riley, excellent. And here is it my favorite telescope? I don't know, they're all my favorite, but this is the newest telescope up there, where a team of students, including students like Riley and myself and a gentleman who works up at Pine Mountain, we helped construct this telescope over the last couple years. This telescope has got a lot of different names, the Robins, but my favorite name for it is Darth Vader's telescope, because it's evil, but in a good way, if that makes sense. And this is the telescope that we used to observe asteroids. And what we're going to talk about here for the rest of the period is how we have obtained some data up at Pine Mountain with that very telescope that you're seeing. And what do we do with that data? And what can we learn about the objects that we observe up at Pine Mountain? And Riley, maybe we can turn it over to you and see if you might want to show us the poster that we put together about this project, which we call the Asteroid Light Curve Project. Take it away, Riley.
Yeah. So this is one of the projects we've been working on for the past few years, and it's been relatively cool. We've been wanting to 3D model asteroids based on the amount of light they reflect. So that's all light that's reflected from the sun that hits the asteroid and it comes back to our telescope. And it's interesting because a lot of these asteroids that are out in the asteroid belt between Mars and Jupiter, a lot of these are, I guess, more hot dog shaped than rather spherical that you might think. And that's because they're rotating really fast. So a lot of these asteroids are in a class that are called rapid rotators. They're rotating once every like 6 hours, and they're the size of Mount Hood. So they're like 30 kilometers wide.
Yeah, so 30 kilometers is about 20 miles or so. I think we might have even determined it was 2 Mount Hoods. Take 2 Mount Hoods and smush it together, and that's about how big this asteroid is. And then how fast is that thing rotating on its axis?
Once every 6 hours, say.
Once every 6 hours. Oh my gosh. So if you can imagine, that's a massive rock that's spinning quite fast. up in space. And that's one of the targets that we've observed. What's the name of the target that we observed in this poster?
572 Rebecca.
572 Rebecca. So the name of the asteroid is Rebecca, and it turns out it's the 572nd asteroid in this big list that was put together a couple hundred years ago. And so there's the target that we selected. And as Riley mentioned, asteroids aren't spherical. They're not baseballs, or they're not basketballs. They're more like potatoes or peanuts. And that's important for our project. Riley, why is that important for our project, as a matter of fact?
So one of the things that we're able to do, because it's hot dog or potato shaped rather, that you were saying, the asteroid reflects different amounts of light depending on the angle you observe it from. So like you could say, take this stapler here as a demo. And when there's areas of more surface area that are reflecting more sunlight, there's more brightness. And then as it's tumbling through the sky, it gets to points where there's less surface area that will reflect less amounts of light. So that turns out to be a pretty repeatable fashion that we could graph and turn into a 3D model.
Interesting. So let's see. So the asteroids are rotating every 6 hours or so. So how often would you take images of the asteroid when you were doing these observations? How often did you take the images?
We would take the images over a course of 6 hours, or about the whole size of the rotation period.
Okay.
And over the observing period that we're talking about in this poster, we took 605 images of the
So
asteroid.
605 individual images of the asteroid. And actually, just roughly how long did each one of those images last, or how long did those images take?
Around 30 seconds or so.
Oh, there you go, right on. So each picture, you looked at the asteroid for 30 seconds, and then we ended up taking 600 of those pictures over the course of a couple nights. Yeah. Oh, so that's actually a pretty fair amount of data that goes into a project like this. And what comes out the other end of the project? What's your final product in some sense?
So in some sense, it's this fluctuation of fluctuation of brightness because it's tumbling through the sky,
Yeah.
which is modeled by this curve here that we have, which is called a light curve.
Light curve, okay. And I guess that's because the light is varying that we're getting from the asteroid. Gotcha.
Yeah, and so I for the remainder of the time, we're going to kind of go over this demo of how you create a light curve like this, how you measure the brightness of an asteroid, and how you even find the darn asteroid in the field.
That sounds great. We'd love to see a little bit of practical use that you did.
So one of the ways we can start to reduce the data is to find out how to measure brightness of an asteroid. So one of the ways that we do this is through relative aperture photometry, where photometry is a method for measuring the brightness of an object in the sky.
Yeah, so really that's what the word photometry means. It means, can we somehow take a picture of something and then measure its brightness with numbers, quantitative, big word, quantitative. But how can we measure the brightness? Gotcha.
So we do that by selecting different apertures to place around the source target. So this red aperture here just encloses the asteroid, say.
So really, so the white spot is the target. There you go. So when we're looking at a picture like this, each of those little white spots that you see, those are stars or an asteroid. And we want to measure the brightness of it. So we use this thing called photometry, and we put those apertures down. Thank you. Go ahead.
Yes. So, and then we have different size apertures to be able to subtract the background noise that's in the sky along with the asteroid. So that's a good way to, I guess, calibrate the data.
Gotcha.
And one easy way that we implement this aperture photometry is through a program called MPO Canopus.
And that's what we're going to see now, I think.
Yes. Let me pull it up here. So one way to look at the image is to open an image.
Mhm.
So
Oh my
this-
gosh, look at all those files. So what are we seeing right there on the screen, that
The-
list?
these are the 605 images we observed of the asteroid in
Gotcha.
a format called FITS format.
Mhm.
And what is the FITS format exactly?
Yeah, it's a file format. It's something similar to like a JPEG or a TIFF or a GIF or it's just a certain type of scientific file name. That's the way I'd call it.
So we can load the image into this program that we're using.
Right on. So now hold on a second. So there's one of the pictures that we took, and what's the audience seeing there?
So by and large, they're seeing a bunch of stars that are out in the field, stars and galaxies and stuff that more or less come up as white dots on the screen.
Right. So those are the stars. Yep.
But hidden in here is an asteroid somewhere. So
Buried down in there, one of those spots is an asteroid. All of them are stars except our one target. And how the heck do you find that thing?
yeah, so just by looking at one image, it's pretty hard to find. But what we do has NPO Canopus has a pretty interesting, useful feature in it where you can select multiple files and make a quick GIF of the asteroid.
Oh,
on
yeah.
the fly.
Do that on the fly. Yeah, look. So here you're just selecting some random, about every 10 files or so. Pick one. Gotcha.
And then it loads in all the files so that we can make a quick visualization of the sky over like an hour to see hopefully a dot moving across the sky.
Right. And that's because, let's think about this real quick, because the asteroid is in our solar system and it's also orbiting the sun. So it moves with respect to the background stars. And that's what we're going to be looking for here. By the way, that was pretty neat. As I was talking, we saw the program load up all those images that you selected. And right now it's doing a little calculation in the background to make the movie.
Yeah. And then you can hit start here and it makes the
Oh,
movie
wait a second. There we go. There's the movie going.
of the sky over a period of about an hour or so.
Hour or so.
And then you can look through the frame. And then if you notice it here in the middle, there's our asteroid that's moving.
That's pretty cool. So you should go ahead and circle it with your cursor again real quick. And now there's two things happening, folks. The whole frame is sliding a little bit just because we did this real quick for you. But look at that asteroid moving with respect to the stars. And that's a sure sign that that's the target that we wanted to observe in this particular image. That's cool. And by the way, Riley just did that live just right now. The computer made that GIF for us right now. That's pretty slick, man. So now we know which little white spot is the target. My gosh, what do we do now?
I can show some other GIFs from the night as well, just to give everyone a little bit.
Yeah. Let's show them the longer one. Oh, there we go. And so there's the asteroid that's moving.
And this is over a course of about 6 hours or so.
Yeah, so that was a big jump. So that was a few hundred frames that were in that particular that little video that we just saw. That's pretty neat seeing the asteroid moving across the screen like that.
And so I guess the next step is just to start reducing the data.
Yeah, let's see if we can't create a little, well, maybe try and make a little light curve, huh?
Yes.
And so, by the way, folks, as you're watching, what you can see is, now Riley knows this program real well. So, he knows where to click and things like that. But you know what? This is just a Windows program. Look at Windows Explorer there. There's nothing very difficult about this. Now, it's a complicated program, but once you learn how to use it, it's pretty straightforward, as a matter of fact. If you have some basic computer skills, you could absolutely sit down and learn how to use this program called NPO Canopus.
Then we can go in the field here.
Okay.
And start to create the light curve by selecting where the asteroid is in the frame, which I'm not having to, oh, there it is.
All
I
right.
almost lost it in the frame.
I was going to say, and by the way, folks, remember, Riley has spent many, many hours already looking at these images, so he knows right where the asteroid is. That's why he can pick it out like that. Oh my gosh, how'd you know it was that one? Well, we've looked at this star field for many hours, so we know which one is the asteroid already.
So this is the asteroid that we saw in the quick GIF there.
Yeah.
So we can put our aperture around it to be able to measure the brightness. You can kind of see in the zoomed in picture in the middle I'm placing the aperture around the source target. the
Yeah, and
asteroid.
you want it kind of centered there in the middle, of course.
And then one other nifty thing we can do is compare it to stars of constant brightness in the field to be able to reduce, to take out some of the noise that's in the, from due to atmospheric effects and light pollution. I'm trying to think of other ones.
It's mostly, yeah, it's atmospheric effects, you know.
Mhm.
You want to have, we know that the brightness of the asteroid changes. And so we want to have something that's constant that we can compare the changes to.
Mhm.
And that's why we call it relative photometry, because we're measuring the brightness of the asteroid relative to some stars that happen to be in the same images.
So then what I did there, I selected the first image in the series of images that we're gonna look at, and then I can select the final image.
All the way down, there we go. So here's a new image.
So then it loads up our final image here, and then you can see the asteroid has moved
Had moved, yeah.
across the field during that time. So, and then you can do some maybe more technical behind the scenes things to align the system up. Yeah, bear with me here. It's a little.
That's okay. No, this is part of it. We'd like to, it's fun seeing you, you know, and what's interesting is this is kind of the process of research. Riley was not nearly as good at this when he first started. Turns out it takes a little while to learn how to do it. But as you work with the data, you get more and more comfortable with it, and with the programs too. You know, you learn the program and you learn how to do it a little more quickly.
And of course, it always every once in a while throws up these weird errors I've never seen, and that's kind of why we don't like these kinds of programs for some reasons.
Yeah.
But by and large, it's really helpful.
Yeah, it really helps to automate the process, and that's been important because, like we said, we had 600 pictures, 600 images, and what we didn't want Riley to do is to try to do this manually, where he had to measure everything 600 times. And so by using the learning how to use the programs, we can do, you know, be much more efficient with the effort, which is real important.
So then what I just did is I selected just 50 images to look at right here. So I can just let it run. So it identifies the two stars that we use to compare to the asteroid and
Right.
the yellow asteroid here.
So the asteroid is the one that's in the yellow, and then our two comparison stars are the red and the green.
Yes.
Gotcha.
And then I can just hit play, and then it goes along the frame and measures the brightness of the asteroid for each of the 50 frames that I just
Interesting.
selected.
So now every time you see a new image flash, that's reading another, there you go. You can see that's reading a new frame and then automatically making the measurements for us. That's quite slick.
And one thing that we've learned that this saves a lot of time versus doing it manually as we had done previously. So writing down all the data values for brightness in a big Google spreadsheet is not nearly as fast as this program.
No, that's what we did. The first time we did it by hand, and it took so long that it was worthwhile going out and researching different programs that would teach us how to do it automatically. And by the way, that's very common in many different types of science. We're working in an era where the software is so good, it's very worthwhile to go out and try to find some programs that will help you with your data analysis. This is pretty slick because we can see, and we're already 42 files through the 50 files. And so it's really quite fast.
Okay. So it spit out an error for us here. So, you know,
Okay.
we're doing this live, so it's a little bit iffy, but
Yeah.
in normal circumstances, it would go through all the files, measure the brightness, and then what we can do is we can go look at the output of that. So I did this beforehand. So you can see there's a brightness value for each of those 50 files that we just looked at.
That's pretty cool.
And you can see the relative change in the magnitude is about 0.1 magnitude, or
Okay.
a decent amount.
Yeah, that's
not through
bright.
the noise.
Yeah, let's see. You could not detect that with your eye. By the way, the thing's way too faint. We can't see it with our eyes anyways, but we couldn't detect the difference with our eyes. But clearly the computers and the cameras that we're using are so sensitive, they can pick up those variations quite easily.
And this is only one section of the data. We only did 50 frames out of the 600.
That's right.
But-
What do you have the full light curve to show maybe?
I have it on the poster that we're
Yeah,
gonna
let's
present
look on the
with this.
poster and show you what the full light curve looked like. Oh my gosh, there you go.
So this is when you put in all the data and then fit it to a curve, kind of what it looks like.
Yeah, and you can see this particular asteroid is what we would call very periodic. You know, you got a nice sine wave looking there. These nice, peaks and trough within the brightness variations. So that's pretty slick. So in the last couple minutes, what can you do with a light curve like this? Once we make a light curve, what can you produce?
So the program we were just using has another additional feature that works to 3D model these asteroids. So it takes input from the amount of change in the brightness and the rotation period that it detects, and I think that's it, and the overall shape of the light curve, and then it works to make 3D models like this. I'll bring it up here.
Yeah.
So this is a 3D model of that light curve that we just produced.
That came from the data, our data at Pine Mountain. That is slick. It's really neat to see it moving kind of in motion here too. And let's remind the folks what we're seeing here. This is a rock that's about 20 miles across, which seems big until you realize it's about 200 million miles away. 20-mile rock, 200 million miles away, and we can determine its shape just by watching and measuring how it changes the brightness that we see. And I think that's pretty neat. That's a kind of a really an interesting and cool way to show the power of science and the power of observing and understanding your data in a real way. Oh, Riley, can you spin that around for us a little bit?
So then this is another version of the 3D model that we made that we can move around and look at the structure of the asteroid.
Yeah. And so as you can see, for sure, that asteroid is not spherical like a basketball, but a little more squished. To me, that looks a little more like an almond or something like that, maybe. Well, look, folks, Riley, go back and show the full poster again just for a second to wrap up with everybody. And so, folks, what you can see here is Riley and a team of students that's listed up there at the top have done a lot of work to produce this poster, which will be presented at the Undergraduate Research Symposium tomorrow. As a matter of fact, we're going to talk about the poster in one of the sessions. And quite often, this is the sort of item that you produce with a research paper, with a research project. And what we found is that our results are so interesting that we're going to keep compiling more data. And then in the end, we're going to see if we can write it up and maybe publish an actual paper about this, which would be great for all the students and everybody involved. So let's see, it's 28 after, so we only got 2 minutes left. And so what I thought we would do is just kind of wrap up here and say, Riley, thank you for presenting and thank you for putting together a great poster. We're looking forward to having it presented tomorrow. And we're absolutely open to any questions. If the moderators have any, or there's anybody in the audience that would like to ask a question. If not, that sounds fine with us too. Don't feel locked here. Excuse me, we're ready to cut you loose and go on to the next section. But Riley and I are going to hang out here for the next minute or two just to make sure. So thank you, everybody. And go Ducks. Nice, throw the O. So look, let's you and I hang out for a second, and if we have any questions, if not, we'll cut off here in a minute.
Okay, sounds good to me.
But that good looking poster, man, I think it came together really nice.
Yeah, the help from the design major really.
And that was cool. And we'll just make folks know that we have a pretty diverse team we have physics majors, we have a history major working on the project, and we also have a student who is a public relations and design major, and she really helped us make the poster look good. And so we appreciated that lots of different folks can contribute to a project like this. And we're proud of the big team that has worked on this project for the last couple of years. And we'll continue to work on it even as we move forward. As Riley becomes a graduate student here at the University of Oregon, we're going to try to keep him involved too.
So I don't see any questions here, but I have two real quick. Just as
Yeah,
we
yes, sir,
close
Michael, what you
out.
got?
The first is on the light curve there, you have a couple of sections where there isn't data. And so I was wondering if you could explain a little bit why that is.
Yeah, Riley, go ahead.
So there's a few reasons because of that. So one of the main reasons is that we only have about, what do you say, 6 or 7 hours of nighttime to be able to observe the full light curve. And there's a few times in there, like this GIF that I have on my poster where there's an occultation with another star where we're not able to get data at certain points along the light curve. And there's also other factors like I think cloudy
in for a few minutes, you know. There's also human reasons that at one point we left and didn't observe for half an hour because we were doing other things at the observatory. But that's a great question, Michael. And our goal is as we move forward is to produce more complete light curves. So excellent question.
And actually, one additional point to that is we have an international collaboration to kind of help minimize that factor. So our international collaboration is in Kobe, Japan, at Kobe University. And one of the things that we're working on is having this, what you would call concatenated observing. So once the sun rises here, the people in Kobe, Japan, pick up the asteroids and start observing right after we do. So they can continue filling in parts of this light curve from their end.
Awesome. And then I was just curious, is the background of this poster actually one of the pictures that you took?
Good
Yes.
eye. What an eye.
Yes, so I think the asteroid's I think in the middle here, right behind the.
Yeah, I think the
7.
asteroid itself is hidden behind one of the frames. But this is this is Dr. Fisher, and my that's sort of my influence on the students. I love having a poster that has a nice picture in the background, and then with the data and the analysis overlaid on top of it. Now, there's lots of different ways to do it, but we like this style. We think it looks good.
Awesome.
Thanks, Michael.
Yeah,
Well,
thank you guys.
Yeah, we'll wrap up. Thanks, everybody. Please let us know if you have any questions or you're interested, and thank you for the opportunity to speak to you.
All right. My impression is that I'm just leaving this open, so y'all can hop out whenever you want.
All right, good deal. Thanks, Michael. We'll talk to you soon, buddy.
Thank you.
Thank you.
Riley, thanks a lot. I think I just got a text from Alton. Oh, well, Alton just came over. So look, come on over whenever you want, buddy.
Yeah, I'm heading to campus in 10 minutes to go
We'll see you soon.
solar
We'll be around Willamette for the time being.
Okay.
I'll tell you what, if you don't, I think about 2 o'clock, we're probably going to walk over to LLC, but right by Duck's Bistro.
Sounds good.
Excellent. See you then.
Hey, Michael.
Yeah.
For the second session, or did you want me to stay on or come back, or how did you want me to do that?
I'll be honest, I don't know. I'm pretty sure I have to leave this open.
Okay.
But I'm pretty sure that you and I can go ahead and just turn our cameras off, and then we can come back. Yeah, when
That sounds
the
good.
next one starts.
I was also going to ask you, I think there were no attendees in the session. So are they posting it somewhere to YouTube or?
Yeah, I believe that this is for sure recorded, and I'm
Mhm.
pretty sure we're going to be posting it somewhere on YouTube. I don't know if it's the Undergraduate Research Symposium or
Mhm.
sales website or whatever.
Okay, that sounds good. I was just thinking I felt bad that there were no questions. I had some questions, but like I thought it was interesting, but I didn't want to like I can't ask a question since I can only
Yeah,
answer them. But
yeah.
that was pretty cool.
Yeah.
Okay. Well, I'll stick around here then and be back for the next one.
Sounds good. All right, so you can go ahead and get started whenever you'd like.
Okay.
This is being recorded too, so we can post it up on YouTube later, and we'll go ahead and filter any questions to you that we get.
Okay, I need to share my screen. Okay. Do you guys see my presentation?
Yes.
Okay. Give me 1 second. Still 1 more second. So I can see so I can see questions that come up. Almost ready. Okay. Let me put laser pointer real quick. Okay. So hi everybody. My name is Armand Garcia, and welcome to my demo today. Today we're going to look at my journey to grad school, which consists of oxygen, sulfur, and many other items. So just a quick few details. I'm a second-year graduate student here at the Department of Chemistry / Biochemistry. My personal interests in chemistry include like chemical biology, bioinorganic chemistry. I'm co-founder and co-president of a student-led organization here at U of O called Alliance for Diversity in Science and Engineering. And I currently have my bachelor's in biochemistry, and I also got my master's in chemistry. So just a little background, my undergrad was at Cal State Fullerton. Then I went on to do my master's at Cal State LA, and now I'm here at U of O. But it was kind of an interesting journey. And so I kind of want to show everybody how it all began. So looking back, I was in a lot of your shoes back in high school, which is I graduated from high school about 10 years ago. I took many honors classes, AP classes, and I didn't know what I really wanted to do at that time. And I think that's the case for a lot of people when you're at the end of high school and trying to figure out what you want to do. So back many years ago, I applied to many universities. I applied to UCs, Cal States, private universities. But realistically, I had no idea what I was doing. All I knew was I thought it'd be pretty cool if I worked for Lego. I didn't know doing what or what I was really interested in, but I just thought it was really cool. So after applying to like numerous universities, I came down to two options. I got rejected from many places, which may happen, and it's totally fine at the end. It's okay where you go and wherever you want to study. I had to either decide between attending Cal State Fullerton or Whittier College. And there were actually several pros and cons between where I wanted to attend. For example, at Cal State Fullerton, back in 2011, when I first started, tuition was only about $6.5K a year, which was financially reasonable to me at that point. It was very easy for me to change my major, and there was numerous opportunities. But realistically, thinking back at the cons, there wasn't really a lot of big cons to me. These are very minor and shouldn't be a big issue to wherever you want to go for college. But I was really unfamiliar with the area. It was called a community university, which isn't necessarily true. Or I was going to attend Whittier College. And some of the reasons why I wanted to attend this private university, I just really wanted to run track with my friends from high school. A lot of my friends were going there and we all ran. So I thought that would be really cool. And I would be able to immediately begin whatever major I wanted to start. But I didn't know what I wanted to major in. And so that was kind of like a big idea for me. How was I going to start something that I didn't know what I really liked? Also, looking at some of the cons back then, it was about $40,000 in tuition a year. Now it's $50,000. And that was kind of a big item that I had to take in consideration if I wanted to attend there. How was I going to be able to afford this very large tuition? And I also had to take in consideration after 4 or 5 years, how expensive is this going to be to me in the long run? So between these choices, I decided to go to Cal State Fullerton, and starting college was pretty difficult. I went from going to like a small-ish high school to a very, very large university with over like 30,000 people, and it was brand new city, and I was commuting, and this was like a whole brand new thing. But what I found was starting college can be difficult. In fact, in my first set of courses, I took an art class, I took an English class, a geography class, and I took college level algebra, and I didn't pass it. And that's when I realized, oh snap, this is a little bit different. And that was kind of like a wake up call. I had to get my stuff together. But I was kind of excited because I was like, okay, I messed up. I have to fix my stuff, figure out what I want to do. And I just kind of thought eventually I'll figure it all out and it's just going to hit me. Well, a year later, starting my second year, I hadn't really committed to a major yet and I didn't know what I wanted to do. So I went to go talk to academic advising. There are usually programs on most universities, or if not all, where you can kind of talk about what do you want to do, what do you like, try to figure out what kind of major you want to go into. And from my few meetings with academic advising, they had mentioned, I like science, I thought it was cool, and they're like, okay, you should major in biology and chemistry. I was like, okay, like I was like, all right, I didn't really have a second thought. But upon going to the chemistry department, I met with Professor Chris Myers, who was the chair of the department, and he said, taking on two different majors at the same time as starting into my third year would take a little bit too long, and I should just study biochemistry. I was like, all right, I guess I'm going to study biochemistry. And realistically, I just thought it sounded really cool. And so I took some introductory courses, and I didn't do too hot. I got mostly C's. I only took 3 classes, each had labs, and I was like, okay, my GPA hit low, probably around 2.3 at that point. But after getting straight C's in a single semester, I was like, okay, I got to get my stuff together. And eventually I did. I figured out what I had to do to get better. I still struggled all throughout my undergrad, but it's totally fine. So I started my third year of my undergrad. I had 0 credits in my major, and I had to take at least 3 science courses every semester for the next 4 years in order to graduate by my 6th term. So a lot of my undergrad consisted of taking many chemistry classes. I took some biology classes, I took some physics classes, and I took some math classes. And it did take up a lot of time. But aside from classes, I also got into research at Cal State Fullerton. When I was attending, it was required for students to complete X amount of units to graduate. So I did do some undergrad research. I did chemical education. So I did some studies on how students use like online tools to kind of help themselves learn and develop fundamental understanding of chemistry. And so it was really fun. This picture is actually a picture of me and my colleague, Leslie. We actually went to go present at UCLA, which was a lot of fun. I also got to present at San Diego. I also presented at numerous other universities, such as Cal State San Marcos, Fullerton. And it was really cool because at these conferences, I got to see what other people do as research. I got to meet other people who also do research as undergrads or where they wanted to go to. And I got a broader sense of what other people are going through at the time. But after a while, undergrad ends and you have to figure out what you want to do afterwards. I wasn't quite sure. It was around my sixth year, the beginning of my 6th year. My GPA was around 2.7, 2.9, not too solid, but totally fine. I did a lot of research presentations. I had a couple of years of teaching organic chemistry, which is one of my favorite subjects. But I also want to know, I also knew that I wanted to go into a new field. I liked what my research was, but I wanted to try something new. But it's hard to decide what you like when you don't know what exists. So luckily, I had a professor, Professor Hal Rogers at Cal State Fullerton. Here we are matching in our chemistry shirts and hair. He was an organic chemistry professor at Cal State Fullerton, and he was always supportive of whatever I wanted to do or any crazy research ideas. And I told him, my GPA I struggled with. I liked the idea of grad school, but I didn't know what was available. And so he recommended that I do my master's at Cal State LA. He actually did his undergrad at Cal State LA, I think in the early 70s. So I was like, okay, I'm going to apply to Cal State LA. And I got in. And there's a few different reasons why I want to do my master's at Cal State LA. And so some of these reasons were I wanted a new research experience. I didn't know if I wanted to do a PhD. I didn't know what it really consisted of. I didn't know where to apply, how to apply, what I should even look for in a program. But most importantly, I didn't know what type of fields of research I liked and what I didn't like. So attending a master's program, some of the few details for this program, I had to maintain a GPA of over 3.0, and you get to take advanced courses in chemistry. This doesn't necessarily mean they're more difficult, but they're more specialized. And I think it's really cool because you will take a class where the professor that's teaching it has done research in that field for several years, and it's actually a field that a class that they developed themselves, and it's material that they like and they've done or know people who found these types of chemical interactions and stuff. I also did like a literature seminar, which not all programs will do, but typically you will actively perform research of some type, and also you will write and defend a thesis. Here's a picture of me with my PI for my master's, Professor Selke. This was immediately after my literature seminar. That was very exciting. But what I got out of my experience from Cal State LA, I got to really understand what kind of chemistry exists. I got to do some really cool research, and I was also able to get 2 different publications. My main project mostly focused on how like these metal sulfur inorganic clusters reacted with excited forms of oxygen, and that was really cool. Additionally, I was part of a project that looked at the cation pi interaction, so we kind of got to see how these natural interactions that occur in our bodies may actually protect us from reactive oxygen species, and that was really cool. I also had the opportunity to present some of this cool research in the Philippines. It was a wild turn of events, but my lab mostly consisted of just myself, my colleague David, who's now at Caltech, and my PI. And originally, I had applied to come give a poster in the Philippines, and then it became me giving a talk, and then my PI getting invited, and then my friend also got to come along, and it was a really fun experience. And that's actually one of the cool things about doing research. You will have the opportunity to give presentations in really cool areas. Sometimes you will go to like California or the East Coast, Boston, Texas, Hawaii, or even out of the country. And that's some of the really cool things I liked about actively performing research in graduate school. Now, taking all that into consideration, it's sometimes really difficult to decide where you want to go to grad school. So typically, what will happen when you attend grad school, mostly in a PhD in STEM, you'll work directly with a professor in a field that's really specialized, and you essentially get to become an expert in a given field, and it's really cool. Here's actually a picture of me when I visited the University of Oregon. This was 2 years ago, right in the middle of a giant snowstorm. So all of Eugene was covered in snow, and I think it was actually my first time ever seeing snow, coming from California. And I just thought it was super cool, and like nobody was on campus, and I got to see the really cool things that University of Oregon offered. So at these visitation weekends, so I'll backtrack. Once you get accepted to a graduate program, you will typically visit the university, and you will it'll be a weekend, or some I hear even go for 3 or 4 days, where you will visit the university. You get to meet everyone in the department. You can tour labs. You get to meet other people who will be part of your cohort, and you also get to learn more in depth about the program and living in a brand new city. So the first thing of my first year of my graduate experience, and like many others, you have a lot of priorities. Your first priority, you will typically TA a class, so that way, so in those situations, you may assist a professor in grading, doing homework, holding office hours, or you might be the head of a lab where you have to show students how to like do experiments and then grade and so on and so forth. Also, your second priority is research. So at University of Oregon in the chemistry department, I had the opportunity to work in 3 different labs. So every quarter I worked in a different lab, and that gives you a broad range of wet hand skills, and you also get to learn more about research that's just occurring in your department. And third priority is taking classes, not lasses. I should have noticed that. And at the end of the term, at the end of your first year, I joined the lab. So here's just kind of a representation, thanks to Lego grad student, kind of showing what my first year and kind of second year looks like. Many meetings via Zoom, but more popularly, you will be doing a lot of reading and studying. And once you're done reading and studying, you will do more reading and studying. So after my first year, I committed to a lab, and I am currently in Professor Mike Poos' lab. And the general theme of our group is to investigate reactive sulfur species in biological systems. Just kind of broadly looking at this image, we can see that sulfur is actually in many different biorelevant molecules. But most importantly, a lot of our studies are focused on H2S, or hydrogen sulfides. And there's several reasons why we look at H2S. More specifically, H2S is found in many different biological systems. We see it in the brain, the lungs, the heart, stomach, kidney, liver, large intestine, and in most cells. And in addition to just sulfur compounds in general, a lot of these reactive sulfur species we consume on a daily basis, such as DATS, or diaryl trisulfide, which is a molecule we will see in garlic. And studying these types of molecules can be really difficult. So what we try to do, we try to develop like these model systems so that we can study these reactive sulfur species in very simple manners. For example, this ONB cage molecule was actually activated by light. So we shine a little bit of light and we can see how this molecule produces certain sulfur species, and we can try to study these systems. So from our research, this is what a typical Monday or Wednesday for me is. Every Monday we will have group meetings. So we will have someone will give a presentation. We will have research talks, practice talks, or technique talks. For example, earlier this quarter, I kind of gave a talk on a literature paper. It's these gold nanoparticles, these gold molecules that were actually have been studied to treat COVID-19 symptoms. Additionally, last quarter, I also gave a talk on how these cool metal-based complexes have actually been used to study, studied for their antibacterial properties. From these talks, we also have technique talks, but most importantly, at the end of every talk, we always share pictures of our cats. It has kind of been tradition, as also everyone in our lab has a cat. So it's very exciting to see that at the end of every talk. Additionally, we also have subgroup meetings. So in these meetings, we'll have a few people kind of talk about the research, what's been going on, present recent experiments, try to again, understanding of the results, what it means, and the greater implication, and try to decide where they're going to go next. So just a couple quick photos. So recently, the whole floor of our department was actually remodeled, and we're in these brand new labs. As you can see from my bay, it's not very tidy as I would like it to be, but we have these brand new lab spaces. We have these brand new windows. This is the view that I had a few Fridays ago, and being able to see Oregon and all its beautiful sunshine when it's around is really exciting while I'm doing experiments for multiple hours. But kind of taking a deeper look into some of my work consists of, sometimes I get to work with these really colorful compounds. Sometimes I have these bright white powders, these dark blue dyes, pink, yellow. I'm not sure what shade of color this is, but sometimes you get to work with these really cool compounds. Sometimes you have to figure out how to make some stuff. So down here, you can kind of see me mixing, testing out different approaches to make my desired compound. Sometimes you get to grow crystals. Here's actually a crystal that I grew several years ago, and that was really exciting to grow. Or sometimes your syntheses or experiments don't quite work out, and you form 3 different products, and you have to figure out why did I not get one, and how are you going to isolate one of them? It can be fairly difficult at times, but that's kind of the general experience of going to grad school and getting to do chemistry and science on a daily basis. So some common myths that I heard a lot when I was an undergrad or even in high school about graduate school, or even questions I get from previous panels I've been on. I just like to go through a few of them, as a few quite are not true, and I just want to shed some light on how they actually work out. So first of all, what I hear a lot is graduate school is too expensive. So this isn't necessarily true. In fact, if you get your PhD in STEM, so I know for sure biology, physics, chemistry, math, I'm probably missing a few other fields for sure, it's actually free. I don't pay anything for my degree. In fact, I get a stipend. So I actually get paid to do my research, or I get paid for TAing. I don't have to take a second job outside of this. You will get a stipend for living expenses and everything, and I don't pay a single dollar after this. In fact, my loans from undergrad are the only loans that I will have throughout my entire academic career. I also hear a lot that graduate school will only help you find a job in academia. That's not quite true. In fact, I know many people who go immediately into industry after earning their PhD. And in fact, getting a PhD can help you strong a really good position in industry. And in fact, there are some companies that have collaborations with university. Some industries will have collaborations with universities trying to hire some fresh PhD students. So those opportunities definitely exist. I also hear a lot that graduate school only equals classes. That's not quite true. In fact, you will only be taking classes through your first year. Maybe in your second year, sometimes you can voluntarily take some extra classes. I know I took an extra class during my second year on outreach in science, and that was very helpful. Graduate school is only for students with high GPAs. This is copy and pasted, whoops. That is not quite true. In fact, my undergrad GPA was around 2.8, 2.9, and I still got into a graduate program. In fact, I know many people who had very high GPAs not get into some PhD programs, or sometimes students will attend graduate school with very high GPAs and realize they don't quite like the experience of graduate school and decide to either master out or look into different opportunities in industry. And another big myth that I don't quite understand how it began is that you need to go to graduate school immediately after undergrad. And that's not the best approach in my opinion. In fact, I highly recommend that if you don't know what you want to do in graduate school, that you should take a year off in between those times to kind of figure out where you want to go, figure out what type of research you want to do. I know many people who have taken breaks in between like high school and before they even start undergrad, or undergrad and before their PhD. Those breaks are not going to be detrimental to your success in the long run. And I highly recommend knowing what you want to do before you kind of blindly go into some items. And yeah, I think that's about it. I think we have just a few minutes for any questions. I didn't see any questions or things pop up on the Zoom, so I will end this slide. I'll stop sharing. So if anybody has any questions, I can totally answer them. I don't know if they pop up in the QA or I get DM'd. I'm not sure.
Yeah, if we end up having questions from the attendees, then they'll pop up in the questions that you're looking at. I have a question. What, if you have an idea what you're looking to do after your PhD program with this experience?
Oh, like what do I want to do?
Yeah.
Oh, that's interesting. So there's a few different things. right now I'm really interested into academia, whether it be I go forth into like a postdoc. I didn't get into postdocs, but that's when you, after you get your PhD, you can go work for in another lab, or continue your research experience into either an academic lab, or you can go do a postdoc in industry. I'm kind of looking into that because realistically doing science with like top tier scientists is just kind of cool in my opinion. And so I think just kind of continuing that, and afterwards, I think I'm kind of looking more into working at like a PUI or primarily undergraduate institution, possibly back in California, but that's kind of where my research interest and overall goals kind of are right now.
All right, I don't know if we're gonna get any questions in the next 3 minutes or so. Anybody's got any?
Oh, I got a question. Brian, how did I decide on pursuing chemistry? I didn't really. My undergrad biochemistry just sounded cool. I took a, oh wait, I think I didn't answer it. I ended my last year, I ended up taking like a biochemistry class, and I didn't find it as interesting as I thought biochemistry sounded. And then I just kind of was like, well, I liked organic chemistry, and most of chemistry is organic. So then I went to go do my master's, and I was like, okay, chemistry's cool. And that's how I kind of decided on it. It was just kind of, sounds cool. I'll see how it is. How do I like it? And I ended up liking it. So that was super convenient and lucky.
Well, in order to spare us the awkward silence, unless we have some more questions, maybe we can wrap it up, unless you have anything else that you'd like to add to your presentation.
I think that's about it. People can email me if they have questions. My email is armang, ARMANG, at uoregon.edu. And I'd be more than welcome to talk about any ideas if you're looking to grad school or just even undergrad. That is a very daunting decision after seeing the various paths that people have taken that I've seen in the past several years.
All right. Well, thank you very much
Okay,
for that
no
presentation.
problem.
Hey, Michael, am I good to go?
Yeah, I'm just trying to figure out if I'm supposed to end this or not, but you're free to go for sure.
Okay. Well, have a good rest of your day.
You as well. Bye.
Thanks.